Now, we will discuss various terms that are used to describe statistical distribution. Let's start with the basics. There are several measures of central tendency, and these are likely familiar to you. They are the mean, median, and mode. The mean is simply an average, or the sum of all the values divided by the number of values in some data set. The median is the middle number in a data set when that data set is organized from least to greatest. And lastly, the mode is the most common number in some given data set. So let me ask you a few questions. Which of these numbers would be most affected by outliers? The answer here is the mean. Similarly, which of these would be least affected by outliers? The answer here is the mode. Now, which one of these statistical measures would be best discovered by charting a histogram? Again, the answer here is the mode. Now, what would you do if you were calculating the median and you had an even list of numbers? The answer here is to take the average of the middle two numbers. Moving on, we see that the normal or Gaussian statistical distribution is a bell-shaped curve and that the mean, median, and mode are all equal. The standard deviation is denoted by the lowercase Greek letter sigma and describes the spread of the data about the mean. So how would the standard deviation be affected in a very precise test? Well, it would be decreased, since the variation of the data is lower and the bell curve would be skinnier. However, a precise test may still not be accurate. Now, what would that look like? Well, it would be shifted. The spread is low, but the result doesn't actually reflect the true population. As shown in this diagram, for normally distributed data, 68% of the data falls within one standard deviation of the mean, 95% of the data falls within two standard deviations of the mean, and 99.7% of the data falls within three standard deviations of the mean. As an example, if the mean systolic blood pressure of a population is 130 with a standard deviation of 10, how many of a 100-member cohort will have blood pressures greater than 140, assuming a normal Gaussian distribution? So we can calculate these numbers as follows. We know that 140 is one standard deviation above the mean. And we know that 68% of the cohort, or 68 members, will have values within plus or minus one standard deviation of the mean. Thus, 32 members have values above 140 or below 120. 120 would be here. By symmetry, we can conclude that 16 members would have systolic blood pressures greater than 140, and another 16 would have systolic blood pressures less than 120. The standard error of the mean, or SEM, is defined as the standard deviation divided by the square root of the sample size. Understanding how standard error of the mean differs from standard deviation can be a little bit tricky. Let's assume that you have a population of interest, but you can't measure everyone in the population. What do? Well, you select a random sample of a certain size that you assume is representative of the population. You measure them and then find the sample mean. Okay, now you put these people back into the population and take another random sample of the same size and you calculate their sample mean. Now you can repeat this process as many times as you want. How precisely do these sample means reflect the true population mean? That is where standard error of the mean comes into play. The standard error of the mean measures the spread of the sample means about the true population mean. Recall that standard error of the mean is the standard deviation divided by the square root of the sample size. Therefore, as sample size increases, standard error of the mean decreases. Does this make sense? It should, because this tells us that as the sample gets larger, the sample means become better estimates of the true population mean. Now, is the standard deviation affected by sample size? The answer is no. The sample size has no effect on standard deviation, only on standard error of the mean. What is the effect of sample size on the standard error of the mean? As we said, standard error of the mean decreases as the sample size increases. Shifting gears now, let's talk about deviations from the normal distribution that we just discussed. Take a look at this bimodal distribution. What do you think would cause something like this? Well, you would see something like this when your data encompasses two different populations, and this is called a bimodal distribution. You might think of something like this when considering an age of onset of certain cancers or suicide rates by age. A positive skew in a distribution occurs when there is asymmetry, with the tail lying on the right. In these distributions, the mean is usually greater than the median, which in turn is typically greater than the mode. A negative skew in a distribution occurs when there's asymmetry, when the tail is on the left. In these distributions, the mean is usually less than the median, which in turn is typically less than the mode. What measurement is best used to make sense of a skewed distribution? In both positive and negative skewed distributions, the median is a better measure of central tendency than either the mean or the mode. Also, in all distributions, the mode is the most resistant to outliers in the sample, whereas the mean, standard deviation, variance, and the range of the distribution are all very sensitive to outliers. The median is only slightly more affected by outliers than the mode. If the reasons for these statements are not immediately clear, then you need to spend some time thinking about them based on the definitions of these statistical terms. Okay, let's do a quick flash quiz. Is this a positive or a negative skew? This is a positive skew, and we know that because the tail is on the right, and thus the mean is greater than the median and the mode. Let's try a practice question. A hospitalized patient has 10 consecutive measurements of their systolic blood pressure. Now suppose the largest pressure measured is 125 millimeters mercury, and the lowest pressure measured is 115 millimeters mercury. If the next measurement is 180, which metric is most likely to remain unchanged? Well, using the approach that we just discussed, the mode, which is the most frequently observed data point, is the most resistant to outliers. All of the other metrics will be more sensitive to outliers and thus would be more likely to change. Let's continue now with statistical hypotheses, which allow us to determine whether there is a statistically significant difference between two groups. The null hypothesis is the hypothesis that there is no difference. For example, a medically relevant null hypothesis could be that there is no association between some disease and a risk factor of interest in that population. The alternative hypothesis is the hypothesis that, in fact, there is a difference in the two populations being studied. This would mean that there is some association between the disease and the risk factor in that population. Now, one can create a new 2x2 table with the study results on the vertical axis and the reality of the results on the horizontal axis. Are you starting to see a theme here? When in doubt on a biostatistics question, draw a 2x2 table. Figuring out what goes into each of the grid boxes helps us to define the error. Okay, so let's talk a little bit more about this 2x2 table concept by discussing the types of errors that we can make when evaluating statistical hypotheses. Well, first you can end up with a correct result, which is simply stating that some effect, difference, or relationship exists when one in fact does exist, or you could state that there is no effect or difference or relationship when in fact none exists. In these cases, your conclusion is right. However, type 1 error is incorrectly stating that there is an effect or difference when none exists in reality. In other words, type 1 error occurs when the experimental or alternative hypothesis is mistakenly accepted and the null hypothesis is rejected. Remember, the null hypothesis says that there is no difference. Now, there's always a chance in any sample population that is randomly assigned to two groups that one group will have more smokers or mothers or some other factor. So how do we account for this? The probability of making a type 1 error is known as alpha. This is equal to the p-value that is typically associated with statistical results. At the very least, you should know that the p-value is typically judged against a preset level of significance. Usually, that is 0.05. If the p is less than 0.05, this means there's less than a 5% chance that the data will mistakenly show an effect or difference when none exists, and we call this result being significant. So less than a 5% chance that your sample population happens to be assorted in some way that could affect your results and claims. The lower the p-value, the more confident one can be that the populations are in fact different when some experimental result says that they are. Type 2 error is stating that there is not an effect or difference when one exists in reality. In other words, type 2 error occurs when you fail to reject the null hypothesis, when in fact the null hypothesis is false. The probability of making a type 2 error is denoted by the Greek letter beta. So how can you reduce type 2 error? Well, you can do it by increasing your sample size, and thus increasing your chances of acquiring a sample population that more closely reflects your population of interest. Can you see that type 2 error is related to standard error of the mean? An increase in the sample size reduces both type 2 error as well as standard error of the mean. One more important thing you should know about type 1 and type 2 error is that they are commonly referred to as being false positives and false negatives. Type 1 errors are false positives. The test gives you a positive result, but that is false. Likewise, type 2 errors are false negatives. Here, the test gives you a negative result, but again, that is false. Now, the concept of power is very important in study design. It's related to what we were just speaking about. Power is the probability of rejecting the null hypothesis when it is in fact false. Or you could think of it as the likelihood of finding a difference if one in fact actually exists. Power is an aspect of the study itself, describing how good a study is at assessing that which it sets out to assess. As an analogy, one could say that the power of the judicial system is the likelihood of determining a defendant guilty when he or she is in fact guilty. Hence, a powerful study is one that has a high likelihood of detecting an effect or difference when one is present. The mathematical definition for power equals 1 minus beta, which means that power can also be thought of as the probability of not making a type 2 error. For example, let's say you're flipping a coin. The null hypothesis here would be that this is a fair coin, so there's no real difference between your ability to get heads or tails. Conversely, the experimental hypothesis or the alternative hypothesis would be that heads is actually favored. Now, if you flip the coin 10 times, you get 6 heads and 4 tails. Now, if you only flip the coin 10 times, even if 6 are heads and 4 are tails, you don't have enough statistical significance to reject your null hypothesis because the power of your experiment is too low. However, if instead you flip the coin 1,000 times and get 600 heads and 400 tails, now you have enough power to reject the null hypothesis and conclude that this coin actually does favor head. It's not a fair coin. Now, power depends on several different factors. First, if you increase the sample size, as we just spoke about, you can increase the power of your study. You can remember this with the aphorism, power in numbers. Similarly, if you decrease the spread of the data, and that's represented by the standard deviation, you are more likely to detect a difference if there is one, and therefore the power of your study also increases. Second, if you increase the significance level, or the probability of type 1 error, alpha, you increase the power. There's a trade-off between type 1 error and type 2 error, so if you're willing to accept a higher probability of a type 1 error, you reduce your probability for type 2 error, since power is defined as 1 minus type 2 error. This also effectively increases your power. Now, finally, as the difference in the mean values between groups or the size of the expected effect increases, it becomes easier to detect a difference, and so power also increases. Okay, did you get all of that? I hope so. Let's see with a practice question. Researchers are designing a study to test the hypothesis that a new beta blocker with fewer side effects will decrease the mortality associated with myocardial infarction compared to the standard of care. They want to make sure that they don't incorrectly ascribe a difference between the new beta blocker and the standard of care if there isn't one. Which parameter do they want to maximize? The correct answer here is C. Now, the researchers want to minimize alpha, which is the probability of erroneously detecting a difference when there really is none. Hence, they want to maximize 1 minus alpha. So this sort of required you to make an additional step to get to the right answer.